Hello, good morning, everyone. Sorry, a little late because I add something to the slide for a while, so was a little this one. Okay, just wait for another 2 more minutes so that we will continue later. Okay, so with the analyzation, shall we begin? Okay, so let's continue with the deviation from the behavior in the mixture of solution. Uh, Now, it might seem a little bit familiar, isn't it, from the deviation from the ideal behavior. Yes, previously we have learned that in the mixture of gases. So in this chapter, we are going to have a look from the perspective of mixture in terms of solution. Okay, so if you still remember in gases there, we say that how does ideal gas behave? So the two characteristics of ideal gas are they have almost no intermolecular forces, okay, and their volume is negligible. So are they the same for the solution? So in terms of solution, they are very different. Okay, so nothing to do with the no intermolecular forces or have negligible volume because solution itself in liquid form definitely they have volume which are very significant. So what are they different in? So let's have a look together. So now, sometimes even with two liquids are miscibles, okay, it may not be an ideal solution, okay? So unlike an ideal solution, a non-ideal solution has the following properties, okay? So what are the properties of a non-ideal solution? Now you still remember the two properties of the three postulate of the mixture of ideal solutions are number one, intermolecular forces between AA and BB is AB are the same, isn't it? But in this case, what makes them divide is either they are stronger or weaker. Okay, either they are stronger or weaker. Okay, it might be other one. Okay, so let's say if it is a stronger, then it will exhibit what we so call as a negative deviation, and when it is weaker, later we will study that it has a positive deviation. Okay, so that's what divides from the ideal behavior inside a mixture of solutions, okay? So when this occurs, what will happen is the partial pressure and the total pressure can be higher or lower than expected, okay? So this will be a little bit similar to that of gas, okay? So later we are going to study a little bit about how does these behaviors take place, okay? So with that analyzation, let's have a look at the comparisons between a positive deviations and a negative deviation for the ideal solution, shall we? Okay, so we go to the next one. So now I'm going to introduce what are the negative deviation and positive deviations between the two miscible liquids. So what makes it a negative deviation? What are the examples of a negative deviation? You have HCl, H2O, HNO3, H2O, sulfuric acid, HCOH, phenylenediamine, acetone, and chloroform. So these are a positive deviation. And then for a negative deviation, you shall have a mixture between alcohol, ethanol, alcohol water, ethanol toluene, and ethanol benzene. So teachers, should we memorize all these examples? Actually, no need to memorize all these examples. You just need to understand or to memorize the one that the first two. From here, you can see what causes a negative deviation is usually acid-water mixture. Okay, and what causes a positive deviation is between alcohol-water mixture. So just memorize like this, then you won't be confused by what are the type of examples that give a negative and positive deviations. Okay, so try your best to remember. Okay, so let's have a look together. What caused it to become a negative and positive deviation? So we say that it has a negative deviation when intermolecular forces between mixture is stronger than that of the individual A and B respectively. Whereas conversely, for a positive deviation, okay, you shall have intermolecular forces between A and B are weaker than that of AA and BB respectively. So how do we determine which one is stronger, which one is weaker? Later we have a look together. Okay, and then in the terms of partial pressure of a mixture, so since we say that it has a greater intermolecular forces, what will happen is when you have a stronger intermolecular forces, it's harder to vaporize, isn't it? When it is harder to vaporize, it will lower the vapor pressure. So therefore, vapor pressure is lower than expected. Okay, as intermolecular forces are stronger, hence harder to vaporize. Compared to a positive deviation is where intermolecular forces of A and B are weaker, therefore the vapor pressure are higher than expected. So this is when negative positive is classified in here. It is negative because it has a vapor pressure lower than expected. It has a positive deviation because vapor pressure are higher than expected. Okay. And in here, what happens towards the heat change when you have a mixture which behave as a negative deviation? When it is a negative deviation, the process take place in here are exothermic process. Conversely, in a positive deviation, you shall have an endothermic process take place in the mixture in here. That means generally, if the mixture is this positive deviation, then you feel warm. And then conversely, if it is a negative deviation, it will feel cool. So if you don't believe, you can pour some of the alcohol, wine or liquor or whatsoever, and then you mix with water. See whether you feel the coolness or not. So if you want a better result, you might want to pour inside a steel cup, okay, so that you can feel the coldness and warmness when you mix in between them. Okay, so that is how the heat change take place in between them. Okay, next we are going to have a look at what causes a negative positive deviation. Why does acid water mixture usually cause a negative deviation? Why does alcohol water mixture usually cause a positive deviation? Let's have a look together. Okay, so this is due to, now for example, we said H2O lah. Now, this is the intermolecular forces between H2O and between H2O and HCl individually. Okay, between H2O and HCl individually, and in between water and ethanol individually. So you can see, let's say for example, inside water, so water, as we already learned, it has small hydrogen bond, isn't it? Okay, whereas HCl are held by weak van der Waals forces in between them, isn't it? So when you mix them, because acids dissociate completely inside water, you form hydroxonium and also chloride ion. So if you notice carefully, between hydroxonium and chloride ion, they form ionic bond. So if you still remember the hierarchy of the strength of the intermolecular forces, we said ionic bond is the strongest, followed by covalent bond. Then covalent bond, you have three different categories. We have hydrogen bond, which is the strongest among the covalent intermolecular forces inside covalent bond. Then we have polar intermolecular forces. then dipole, permanent dipole, intermolecular forces. And then we also have temporary dipole or induced dipole intermolecular forces. So that is the weakest among all. So in here, after mixing HCl and H2O together, they ionize to become H3O plus and Cl minus. Hence, the intermolecular forces between positive, negative are ionic bond. Therefore, they form strong electrostatic attraction forces. Whereas for positive deviation, if you notice carefully about how are the intermolecular forces that take place inside water, it is still a hydrogen bond. And actually, not only water is hydrogen bond, alcohol also exhibited hydrogen bond respectively. However, when you mix the water and alcohol together, you can see that it breaks the hydrogen bond inside water. So now water not only no longer interact with only water, it now interact with also alcohol. So this will broken the number of the hydrogen bond inside water, hence weaken the intermolecular forces. Okay, so in another word, after mixing ethanol and water, the intermolecular forces in between water has decreased because they are now interacting with ethanol, hence decrease the intermolecular forces in between them, therefore has a positive deviation. Okay. So in another word, HCl, when you mix together, its vapor pressure is lower than expected because it's harder to vaporize due to its ionic bonding. Conversely, if you mix ethanol and water, because they weaken the intermolecular forces, they have a higher vapor pressure, therefore vaporize easier. Okay, so that is the differences between a negative deviation and also positive deviation. What are the reasons that cause them to have a negative and positive deviations? Okay. Okay, and then we are going to have a look a little bit about what are the changes that might take place inside a positive negative deviation. So in terms of volume of mixture, since mixing a solution causes a stronger intermolecular forces, so when you, let's say, mix 50 centimeter cube of A with 50 centimeter cube of B, so the total volume later will be lesser than 100. So why? Because now when you have a stronger intermolecular forces, the volume is contracting. So when the volume is contracting, therefore the total volume will be lesser than 100. Conversely, if it is a positive deviation, because you have a weaker intermolecular forces, they slightly repel among each other. Therefore, when you mix 50 centimeter cube of A with 50 centimeter cube of B, the volume of the mixture will be greater than 100 centimeter cube. Okay. Why? Because it is expanding when your mixture as they have a weaker intermolecular forces. Okay. Okay. So now, what are the graph or how does it looks like for a positive and negative deviation graph for a vapor pressure composition curve and also boiling point composition curve? So this is the graph of vapor pressure composition curve and also boiling point composition curve. So if you still remember, okay. So let's say now this is a mixture in between. This is a mixture in between this HCl and also H2O, for example. Okay, so this is the vapor pressure for HCl, let's say. Okay, and this is the vapor pressure for water, H2O. Sorry, I think I mixed wrong there. Okay, okay, sorry. Vapor pressure of the water supposedly to be lower lah. Okay, so this is the vapor pressure for the water, let's say, and this is the vapor pressure for the HCl. So HCl has a higher vapor pressure because it's vaporized easily. Okay, so this is a mixture in between them. Okay, this is a mixture in between them. So this type of mixture in here, we call it as an azeotropic mixture. Okay, we call it as an azeotropic mixture. Okay, okay. Now, if you still remember, when I showed you how to draw in between vapor pressure composition curve and boiling point composition curve, now you imagine like you have a line in here. Okay, you are reflecting a line in here lah. Okay, so if you draw a line, you reflect. Okay, so those with a higher vapor pressure, okay, those who have a higher vapor pressure, those with a higher vapor pressure, okay, vapor pressure will have a lower boiling point, okay, and conversely, those with a lower vapor pressure, will have a higher boiling point. So therefore, if we convert it into a boiling point composition curve, so you will expect that water has a higher boiling point. Okay, so this is the boiling point for pure water. Okay, whereas this is the boiling point for HCl. Okay, and inside the azeotropic mixture in here right now, okay, so now this azeotropic mixture has a higher boiling point than expected. Okay, some books you can see that they write azeotrope. Okay, so what is actually the definition of azeotrope? Definition of azeotrope has two key points in here. So what are the two key points? Azeotropic mixture is a mixture where the boiling point is constant. Okay, second key point, where liquid and gas are at equilibrium. By the way, I forgot to label. If you still remember, in the boiling point composition curve, okay, everything above the curve are liquid, and everything below the curve are gas. Okay, and then for boiling point composition curve, everything above the curve are gas, everything below the curve are liquid. In here. Okay, so this is what happened in between a vapor pressure composition curve and also boiling point composition curve. Okay, so this is for negative deviation. So as for positive deviation, so how would it look like? So for a positive deviation, okay, you shall have, let's say, this is ethanol. This is pure ethanol. Okay. And this is for pure water. So water has a lower vapor pressure than ethanol. Okay. So you have a higher vapor pressure, therefore a lower boiling point. Whereas for alcohol, it has a lower vapor pressure, therefore a higher boiling point. Now, if you still remember, same technique. So what are the technique that we use to convert boiling point, vapor pressure composition curve to boiling point composition curve? Just imagine that if you are like reflecting this curve, okay, reflecting this curve. So when you reflect the curve, okay, so when you reflect the curve, what will happen in here? How will it look like? So it looks like something like this, okay, where in here, this is the azeotropic mixture. Okay, and here this is the boiling point of pure ethanol. And then this is the boiling point of pure water. Okay, and as usual, everything above the curve are gas, everything below the curve are liquid, and same goes to here. Everything below the curve are liquid, everything above the curve are gas. Okay, so that is how we are going to plot or to sketch for the negative and positive deviations. Okay, so it is called as, again, I would like to highlight, it is called as negative, okay, because vapor pressure is lower than expected, and it is positive because vapor pressure is higher than expected. Okay, so can you imagine if you have a lower vapor pressure, it is because it has a stronger intermolecular forces. Conversely, for a positive deviation, because it has a higher vapor pressure, because the mixture have this stronger, weaker intermolecular forces after mixing them together. So that is what you have. So teacher, is the azeotropic mixture is random or they have a fixed boiling point. So if you have in here, if you see the definition of an azeotrope, azeotropic is where mixture between two the solution. Sorry, I forgot to mention between two solution. Two non-ideal. Okay. Mixture between two non-ideal solution where the boiling point is constant, first keyword, okay, and the liquid and gas are at equilibrium. Okay, so this is the two keywords that you have to define whenever you are defining the terms for azeotropic. Okay, so hopefully you'll be able to understand slightly better. Okay, okay, so let's continue with the next one. So these are the examples of the negative and positive deviation mixture. For example, water boiling point 100 degrees Celsius, nitric acid 86. So the azeotropic mixture boils at 120.5 and the composition where nitric acid is 68.2. Another example is between chloroform and propanone. Boiling point of chloroform is 61.2. Boiling point of propanone is 56.2. So their azeotropic mixture boils at 64.5 degrees Celsius under the composition of chloroform 80% and propanone 20%. Okay, so this is for examples of negative deviation. As for positive deviation, okay, so you have ethanol mixture is 78.5, whereas the water boiling point is 100. So the azeotropic mixture has a lower boiling point than expected, which is 78 degrees Celsius, and the composition of ethanol 95.6%, whereas composition of water is 4.4%. Another example is between chloroform and also ethanol, where you can see that boiling point of chloroform and ethanol are 61.2 and 78.5 respectively. Their azeotropic mixture boils at 59.4 and a composition of 93% of chloroform and 7% of the ethanol. Okay, so don't worry, if they ask you to sketch this non-ideal behavior boiling point composition curve, they will definitely tells you what are the azeotropic mixture, what are the melting point, boiling point, and what are the composition in between them. So it's up to you to know how to read whether it is a negative or positive deviations. Okay, so you must be very good in reading. So again, I'd like to flip back to the graph just now. For a negative deviation, most of the time we are more focused towards boiling point composition curve. We are more focused to boiling point composition curve. Okay, so you have to label this is the azeotropic mixture, this is the pure A, and this is the pure B, and this is the percentage by mass. Usually you use percentage by mass of the mixture in between two solutions. Since this one 0 to 1 are mole fraction. Okay, so if let's say if A is 0.3, B must be 0.7. Okay, they are contradicting with each other in terms of value. Okay. Okay, so that is for negative and positive deviations for alcohol. For non-ideal mixture. Okay, immediately let's have a look at the effect when you brought them to a fractional distillation. Okay, so later we have a look. So let's have a look at the content. So azeotropic mixture is defined as a non-ideal mixture between two solutions which has a constant boiling point at a fixed pressure, where the composition of liquid and gas are at equilibrium. So depending on the type of deviation, fractional distillation for non-ideal mixture produce different distillate and residue when they are brought to fractional distillation under different composition of liquid. So using mixture in between ethanol and water example, the boiling point composition curve are sketched for a positively divided non-ideal mixture, and they are explained accordingly. Okay, so let's say if you now have a composition mixture between 50% ethanol, therefore 50% of water. So this mixture content, they are not yet azeotrope. Okay, because azeotrope, as we see just now, is 78 degrees Celsius, isn't it? Now our mixture is 50-50. So we are about to have a look. Can we separate this mixture using fractional distillation, like what we see just now? Previously, when we discussed the fractional distillation, let's say inside the petroleum industry. Okay, because in petroleum industry, they are made of mixture of gases or liquid, isn't it? So you need fractional distillations to separate them, okay? So in here, we are also going to apply the same fractional distillations examples inside discussion of the positive and negative deviation. So showing you the first one is a positive deviation where we have between mixture of ethanol and water at first 50% decomposition. Okay, so at 50% composition, so where are the 50%? So if you look carefully, 50% is located at here. Okay. Okay, so this is the 50%. Okay, so I take here 50%. Okay. So now you have 50%. Okay. So now what happens when you boil this mixture in, don't forget now we are still in a liquid composition. Okay, this is a liquid composition. As I told you, everything above the curve are gas and everything below the curve are liquid, isn't it? And this is your azeotrope mixture. Okay, so now what happens when you brought to fractional distillation? So the process of vaporization, condensation keep on occurring, isn't it? Okay, so the process of fractional vaporization, condensation, vaporization, condensation, vaporization, condensation keep on occurring, okay, until in here you can see what is our first distillate when you fractional distillate 50% of the this one. So after series of vaporization, condensation, okay, so eventually we will get our first distillate in here will be the azeotrope mixture. That means the first come out okay, is azeotrope. Okay. Okay. As for the second distillate, if let's say after we distillate out the azeotropic mixture, okay, then we continue its fractional distillations. So when we continue the fractional distillation, which one will be second distillated? Okay, so it depends on the composition. Now, if you see at this curve is what we so-called as bias to the left wing. Okay, bias to the left wing. That means it's going more towards the alcohol mixture, isn't it? Here, so our second distillate, this is water. Okay, I might make a mistake in here. Whereas in here, the second distillate in here is not pure ethanol. Sorry, can I cancel this? It's not pure ethanol. Okay, it's instead of pure ethanol. Hey, oh, this is 98%. Okay, sorry. Okay, for 50%, the 50%, okay, 50% composition, your second distillate will be water. Okay, and then what is the residue? The residue will be impurity plus alcohol. Now, this one you can check on the previous slide, the previous slide there. Okay, you can flip back to the previous slide, see whether they are there or not. Okay, I've already jotted them down. See, I already jotted them down. Water will be second distillate. Okay. Okay, then what happened in the second situation, if you now have 98% of ethanol. So now, where are the 98% of ethanol? Let's have a look together. Okay, so 98% ethanol is, let's say here is your 98% of ethanol, 98%. Okay, this is your 98% of ethanol. So what will happens to the fractional distillation if you keep on, if you brought them to fractional distillation? Of course, the process of vaporization okay, of course, the process of vaporization, condensation keep on occurring. Okay, vaporization, condensation. Okay, vaporization, condensation, vaporization keep on occurring until what? And you can see from here, from the red arrow in here. So I'm going to type out in terms of the text in here. Okay, so I'm going to type out here using the red color so that you can see clearly. So our first distillate will be azeotropic mixture. Whereas in here, see, since you see our this what our graph, our table, our diagram in here is biased to the right, isn't it? So when it is biased to the right, so in here, as a result, later when you continue to fractional distillate, then we shall have a second distillate. Okay. Our second distillate will be pure ethanol. So this will leave our impurities, residue, sorry. This will leave our residue as water plus impurities. Okay, so that is how you are going to apply fractional distillations for positive deviation. So it depends whether you start from the left or you start from the right in here. Okay, so if it is starting from the left, so your first distillate will be azeotropic mixture. Then your second distillate will be water. What is biased to the right, okay? And then if you start at, let's say, 98% of ethanol, okay? So your first distillate will be azeotropic mixture, where your second distillate will be pure ethanol, and the residue is water plus impurity. Now, let's say that this is where STPM question, I'm so sorry to be exam oriented. STPM question only asks for one distillate only once. So if the question said distillate only once, then we say that our first distillate will be azeotropic mixture, then our residue will be ethanol plus impurities. Okay, so it depends on which one has a higher percentage, then that will be the residue. Okay, so that is how we are going to determine the first distillate and second distillate. Okay, okay, so that is all for the discussion for a positive deviation. Okay, so immediately we goes to the second one, which is negative deviations. Okay, so as for negative deviation, let's say we have a mixture in between nitric acid and water. So we start from 40% nitric acid and 80% of nitric acid. So given to you, this is the graph of negative and positive deviations. Okay. Okay, so this is the boiling point composition mixture in between ethanol, nitric acid, and also nitric acid and water. So in here, this is the boiling point for pure water. Okay, pure water. Whereas this is the boiling point for pure nitric acid. Okay, and this is where azeotropic mixture. You must label, please. Okay, and then you also have to label everything above the curve. Everything above the curve are gas. Okay, and everything below the curve are liquid. try to label as much as you can. Teacher, what happened in between? Now, as I already told you previously, what happened, let's say in between here, these are all where liquid and gas are at equilibrium, okay? Okay, so now let's together study what happened when 40% of nitric acid and 80% of nitric acid is brought for fractional distillations. So let's begin with the 40% of the nitric acid. Okay, so let's say this is the 40% nitric acid. Okay. My graph might be a little bit off because the way of how I draw the diagram, but still hopefully you'll be able to understand. Okay, so this is where the 40% of the nitric acid. Okay. Okay, so now we are going to see how the fractional distillations occur for a 40% nitric acid. Okay, so as you can see, the process of vaporization, condensation, vaporization, condensation, vaporization, condensation keep on occurring until you see that in here, your first distillate coming out will be the pure water. Do you see that? Okay. The first distillate in here will be pure water. Therefore, your second distillate will guarantee be a isotropic mixture. Okay, whereas the residue are nitric acid. So this is for fractional distillation if you brought to 40% nitric acid. Okay, so what will happen if, let's say, you brought for 80% of the nitric acid? Okay, so now this is where, let's say, we mark the 80% of the nitric acid. So if it is 80% of nitric acid, so let's begin. Okay, so I use different colors to can see clearly. Okay, so 80% of nitric acid. So this is where your composition start with. So you start to boil them. So when you start to boil them, 80%, so vaporization, condensation. Okay, vaporization, condensation, vaporization, condensation keep on occurring until you can see from here what are the first distillate that you can see in here. So as you can see very clearly, our first distillate when you start at 80%, first distillate okay, will be pure nitric acid. While our second distillate will be isotropic mixture, whereas the residue are water plus impurities. Okay. Okay, so this is what happened if you start at the 80% of the nitric acid. Okay, so again, from the angle from the STPM, if they ask what are the first distillate, what are the second distillate, okay, then you shall say like this. So what happened if the question only asks for first distillate? Then what are the residue? So if the question asks what are the first distillate, if you start, let's say in this case, we start at 40% of the nitric acid, then your first distillate will be the nitric acid, of pure water. Okay, your first distillate will be pure water, then your residue will be isotropic mixture. Okay, if you, let's say, start from the 80% of the nitric acid, then your first distillate will be pure nitric acid, whereas your residue will be isotropic mixture. Okay, so this is how you determine for positive and negative deviations. Okay, so hopefully you'll be able to understand about the principle of fractional distillations. Okay, okay. As for the final part of our lesson today, just a little bit more to go actually. Okay, it is the this is not extremely important, but still it is inside our syllabus. I have to introduce to you. Sorry, this is repeating already. Okay, distillation under reduced pressure. So distillation under reduced pressure are for those organic substances which eventually decompose if you started to heat them. Okay, so when you want to avoid them to decompose, because once you decompose, there is no point for you to undergo a fractional distillations already. Okay, so that is why you need to lower the vapor pressure. So if you lower the vapor pressure, boiling point is lower. However, this technique is not a really suitable technique because if you lower the vapor pressure,